So we're continuing our discussion of network theory. Section 8.3 will be network flow. Network flow. And so as the name suggested, we're going to be thinking about network. Let's just go ahead and draw an example in here. And we're going to have the thing with the flow is that we're going to have a source labeled S. So S is labeled for the source. Notice our book uses the unfortunate SO for the notation, and then also a terminal node T, and so T is for terminal node, and our book uses the idea of a sink, okay, SI. And so then along these, or what connects the nodes, we could think of as pipes, where this is going to be a directed graph, so the flow is moving in a certain direction that we have to define here. And so we can put on some numbers, and these numbers are going to represent the capacities of each of the pipes. Let's see, 7, 2, and 2, 5. Ding, 1, 2, 3. Okay, and so there we go. Now, we're going to think of a flow on the graph as a function. And the idea is the function is going to take in an edge and produce the number. So it takes in an edge, and then it outputs a number f sub e, and so that's the how much of the capacity we're using on the edge. So for example, if I was just using 1 unit of flow on the out of 2 on this edge from S to 1, I would say that f sub S1 is equal to 1, and then I could also use the notation C for capacity, and then S1 for the edge equals 2. And so our book will also, if you see let me make sure here which one's in parentheses first. The flow is in parentheses. I don't know why they do this. So the flow is in parentheses and the capacity is not. And so this corresponds to the flow when you see that, and then the capacity. Good. All right. So what we're going to try to do is we're going to try to push as much stuff through the source as we can. And so the problem that we're going to try to solve is the max flow problem. Okay, so we're going to try to push as much as we can through the pipes while still maintaining some constraints. And so we should probably talk about what those constraints are. Those are really important constraints. So let's see here. Number one, so let's talk about some constraints. Constraints on the flow. Number one, f sub e, so for each edge E in E, so that's our edge set. We have that, gosh darn it. We have 0 less than or equal to f sub E less than or equal to C sub E. Okay, so the flow that you're using is bigger than or equal to 0, but it's less than the capacity. Okay, 2, for every node except the source and the terminal, flow in must equal flow out. Flow in equals flow out. Okay, so that's conservation of flow. We don't want any of these nodes like drinking water or putting water out. And then finally, we could say that the source, the flow out of the source, flow out of S equals flow into T. And I should say the book gets around this by putting an edge. The book draws an edge from T to S. Okay, so we're not going to do that. That's not a standard thing to do. Okay, good. And so this is kind of an interesting set of constraints, because in fact this set of constraints defines a what do we study in this class? Linear programs. So what are my decision variables? So let's see if we can figure out the linear program. So the decision variables are going to be your flow values, F sub E, for every edge in your edge set. Okay? And so we've already said, right, that this part, well, I guess we could go ahead and put that in. Before we do that, let's go ahead and what do we want to try to do here? What's our objective? Our objective function, we're going to focus just on this network here. We want to maximize the flow out of the source, right? So that means FS1 plus FS2 plus FS3. That's what we want to try to maximize. So we're going to try to maximize FS1 plus FS2 plus FS3 such that, and then we just list all of our constraints. So 0 less than or equal to FS1 less than or equal to 2. That's our first edge constraint, right? The next one will be this one. So that's going to be 0 is less than or equal to FS2 is less than or equal to 2. Oops, did I... oh, there it is, 8. Sorry about that. FS2 has to be less than or equal to 8, right? So let's put that in there. And you're probably saying to yourself, oh my God, is he going to talk through every one of those? No. Read the notes. Look at the rest. I'll just draw the last one. F3, 1 is less than or equal to 5. Good. Okay. So those are the making sure the flow is non-negative. Good. Okay. Now, let's take a look at node 1. Node 1. What is the flow in? FS2. Flow out is 1T and 1,2. Let me redraw it. This is the flow in, and this is the flow out and the flow out. So FS1 must be equal to 1T plus 1,2. Let's go ahead and write that. Such that, we'll just draw one of these here. Such that FS1 equals F1T plus F12. And so that's for node 1. And you can read the other ones in the notes. I just wanted to mention this because we're not actually solving this linear program. But you could if you wanted to. Okay. Good. All right. And so let's get back to our problem then. I'm just going to go ahead and rewrite my diagram here. 1, 2, 3, T. Okay, and then I've got these flows coming through. Out, out. Whoops, that one's not there. Down, down. Good. And so we might have something like, let's see, maybe I can just guess. Here's 2, 8, 3, 7 and 2, 2 and 5. Can we just find a flow on this for this diagram? I'll use red for that. Let's just pick one. Here's one. So path 1, we're saying, is going to be S1T. And so the value of the flow is going to be the minimum number on the capacities, right? Because as you go through the flow, right, you can't exceed any of the capacities. So the smallest capacity is going to dictate the flow for the entire edge. That's called the bottleneck. So the bottleneck value Well, in this case, of course, the two capacities are equal, which is called B in some places. B is equal to 2 in there. Good. So let's do a couple more. How about this path here, going this edge and then this edge. So we'll call that path 2. And so what's the bottleneck on that? Oh, and let me draw it here. S3T has a value of B equals 3. Good. And let's do one more. How about the path from here and then down? Do I have any more left here? Let's see, there was 2 left right after the 5, and there's 2 there. So therefore, path 3 can be S23T, and the bottleneck value is 2. And that actually exhausts this 5, right? And so there's nothing left there. And so there's nothing left there. And then there's 6 left here, right? And then I think we've taken up the 2 there. Oops, so that left 0. And what do you know? I think we've exhausted everything that could flow into the terminal, right? So what's the value of the flow into the terminal? 3, 4, 5, 6, 7. Okay, so that was a quick look at finding the maximum path. We're going to formalize this process in just a minute, so that'll be the topic of the next video.